Okay, see Lindelof videos, AP Calculus. Find the upper and lower sums of a region. We're trying to approximate how much area is under this curve. And we have to be really careful about the use of the word area, but I'm just going to use that for now. And if you look at this, we're going to work on what's called a lower sum right now. So this is our lower sum. And what we're saying is this. We're going to use this notation. We're going to use this m sub I here. And I hope you're noticing that this is a lowercase m. And what we're saying is, what m sub I, little m sub I is it says that the minimum value of f of x on the ith subinterval, which sounds like a load of crap to me, but let this be the subinterval of interest right here. And what's the lowest f of x value? Would be this one. Then if I went to the next subinterval, which might be this one right here, say, okay, what's the lowest f of x value? And it's this one right here. And if I kept doing that, I'm just trying to get an idea. If I went to this subinterval right here, what's the lowest f of x value? Well, it's this f of x value, right? Given that f of x is this function right here, and this function in our case is x squared. We're asked in this case to find the region under the curve of f of x and above the x-axis as x goes from 0 to 2. So that's what we're going to do. So we're going to use this left-hand endpoint. If you can see, this is the left-hand endpoint. This actually is a rectangle, this little flat thing. It just doesn't have any area. The next rectangle starts here and goes like this. So it gives us this notation. It says go to your starting point, in our case it's 0, plus I minus 1. Because if you look, this value, this is the A value and this is the B value. This is x sub 0. So if we go to the first interval, we'd have 1 minus 1 is 0, puts us here. We go to the second one, it would be 2 minus 1, it puts us at this one, and so on. So it keeps us balanced there. And then what we want to know is how big is the subinterval? Well, it's 2 divided by n. How did I get that? I got b, the farthest distance, minus the nearest distance divided by the number of subintervals. So we have, this is 2 here, right? This is 2, and this is 0. So 2 minus 0 is 2. All right? So that gets us to right here. So I'm going to start with our lower sum. I'm going to say, okay, lowercase n is the lower sum, where uppercase n would be uppercase s would be the upper sum. And we're going to start to define and say, well, it's the summation of all those rectangles that we're going to count up. So we're going to count up all the rectangles from I is equal to 1 to n, because we don't know how many rectangles we're going to have. And what are the rectangles made of? Well, the rectangles have a height of f of, right, 2I minus 1 over n. So when I multiply this times this, I got this piece right here, okay? And f says that we haven't plugged it into the function yet. Times change in x. Well, the change in x is b minus a over n, because each base will have a width of 2 divided by n, right? So this is our height, and this is our base, and we multiply height times base, we get the area of a rectangle, right? And then we're going to gather up the area of all the rectangles, and this here says that we're going to add those areas together. So that's our big plan. So from here, we're going to do this. We're going to start to put this into cleaner notation. We're going to say the lower sum is equal to the summation of f, but in this case, we know what f is. F is x squared, and we defined our x value as 2 times I minus 1 all over n quantity squared. Why squared? Because I'm plugging it into this function up here. That's where this is coming from, right? So this is the height, and its base is change of x, and we did the work on change of x, and change of x was 2 over n. It's I equals 1 to n. Okay? So I think this actually goes pretty well. It does turn into some algebra, and you have to really pay attention to your algebra here. What I'm going to do, remember that exponents are distributive over multiplication. So 2 squared is 4. 4 times 2 is 8. So I'm going to say I have this. I'm not going to keep talking about saying this is a pain in the neck, but it's 8, right? 2 squared is 4 times 2 is 8. N squared, n to the second is n squared. N squared times n is n cubed. Hopefully you'll see why I'm doing this in a second. And then what I'm going to do is I'm keeping in mind that I also have to square this piece. And I want to be careful because this exponent is not distributive inside of here, right? These are terms, not factors. So I have to actually do that. So what I'm doing on the side is I did I minus 1 times I minus 1. And when I multiplied that out, I got I squared minus 2I, right, plus 1. So this gets us, when we get here, things are starting to get better. Here I'm going to apply some properties here. And one property I know is that I can factor out a constant value. So I'm going to rewrite this way. I'm going to say 8 over n cubed. N cubed is a number, right? The number of partitions. So this is a constant value times the summation of this stuff here, I squared minus 2I plus 1. From here, I know that I can do summation by part. So I'm going to do that now. I'm going to take summation by part. So I'm going to say this is the same as 8 over n cubed. I'm showing you a lot more detail than I guess I might otherwise, but I'm going to take the summation of I squared, is I equals 1, goes from 1 to n. Here's this negative 2. I'm going to factor this out. So negative 2 times the summation of I as I goes from 1 to n, plus this plus sign is this plus sign, the summation of 1. This 1 is this 1 as I equals 1 goes from 1 to n. So, wow, my God, what a pain in the neck, right? So I agree with you on all of that. Now, our goal here is always to get into summation formulas. So we're in sigma right now. We want to get into summation formulas. So we want to go to our summation formulas and see what we can do here. Hold on one second. Okay, so as we keep moving here, I'm going to do this. I'm going to go into my summation formulas. So I'm just going to rewrite this. 8 over n cubed. And then I know what the summation formula is for I squared, and the summation formula for I squared. So I'm taking the summation formulas and I'm figuring out what is the summation formula for this bit right here. And I recognize that I know this thing. It's n times n plus 1 over 2 n plus 1 all over 6. That gives me this part. If this is bothering you, like, what the hell just happened? Then stop for a second. Go back and look at your summation formulas because you have to have those memorized. It's really key. So this negative 2 right here is this negative 2. And what's the summation of I? Summation formula for I is n times n plus 1 all over 2, right? And the summation formula for this is just c times n. This is c, so 1 times n is n. So plus n. So I've come out of sigma form and I've gone into summation formulas now, and I'm starting to pursue this out a little bit. Here it gets to be a royal pain, but I'll do it anyway. This goes to, what does it go to? This goes to negative 6. I'm going to multiply. I need a common denominator, so I'm going to make the common denominator 6. So I have to multiply everything by 3. So if you see it there, and then this will be 6n over 6. It's still n, isn't it? And if you notice, they all match. And that was my big plan here. Because what I want to do is I want to factor out that 1/6, if you don't mind. So I factor that out, more algebra, of course. So it's 8 over 6n cubed, right? And then we're going to do n times n plus 1, 2n plus 1, minus 6n squared plus, whoops, let me do that better. Sorry, let me do that better. Minus 6 times n squared plus n, right? Plus 6n. Good. This is gonna work out great. Okay. So the whole thing, I have to admit to you, the whole thing is a super pain to me, but this is what your professor wants to see, so we have to actually chase it this way. I am going to actually open this thing up a little bit. I am going to open this up a little bit and see what we have here. So I'm going to go ahead and do this bit of math, and as I open this math up, I get this. I'm just going to clean all this crap up, and as I clean all that crap up, I get this. My God, what a pain. First thing, I guess I can simplify this. So I get 4 over 3 n cubed, right? 8 over 6 is 4/3, right? And then I'm going to go ahead and I'm going to go ahead and expand this bit right here. And as I do, I get 2 n cubed plus 3 n squared plus n. That's this times this times this, yeah? If I put this in here, if I put this in, I get negative 6n squared minus 6n plus 6n. I know, stay with me. I swear to you, it's worth it because we're almost at the end of it. It's just a big chase. It truly is. I'm going to go ahead and simplify this out. And as I simplify it out, we get 4 over 3n cubed, 2n cubed, right? But we have 3n squared and negative 6n squared gives us a negative 3n squared, doesn't it? Negative 3n squared. So we got rid of this. We use this and this. Negative 6n plus 6n is 0. It gives us plus n here. Holy schmagoli. So we're almost there. Now finally what we're going to do is distribute all this crap in here. This thing, it's not so hard. It's just a lot to do. So I'm going to go ahead and work that out. If I multiply this, I get 8n cubed over 3n cubed minus, so if I simplify that out, I get minus 4n squared over n cubed, right? Plus 4n over 3n cubed. Let's see what happens here. This goes to this, doesn't it? These two things cancel, don't they? What happens here? This one cancels part of this, gives us 2, right? So you say, okay, Charlie, what did I do all this for? Well, the whole idea of doing these upper and lower sums, the idea of the whole thing is that we can capture the most area, we can be most accurate if we have this infinite number of intervals. So we're going to take this limit. We're going to say, well, what would the limit be if the number of intervals, the number of rectangles, went to infinity? So I'm going to take the limit of this whole thing. Well, you tell me, what is the limit of 8/3 as n goes to infinity? Well, it doesn't change, does it? It stays at 8/3. What is the limit of negative 4 over n as n goes to infinity? So if I take negative 4 over an enormously large number, it gets near 0, doesn't it? And then I'm going to do the same thing here. I have 4 over 3 times an infinitely large number squared. That's also going to be 0. So our lower sum is going to be equal to 8/3. My gosh, not easy. So hopefully this was really helpful. I know it was not easy. I guess what we have to really talk about is all of this algebra, because it's just loads and loads and loads of it. So this is what that looks like. You can expect to see some variation of this on the AP exam. We just have to kind of know what we're talking about. So if you have any questions or comments, please let me know. And if you haven't already subscribed, please do.